Hi there, so welcome back to the second half of term. We have a small video now just to finish off the ordinary differential equations part of the module before we move on to matrices, which is the next big chunk of the module for the second half of term. So I'm just going to go through some slides that we had last time. Last time I went through the theory of this, so I'm just going to summarize the theory. We're considering the ordinary differential equation d2y by dx squared is fx. So a lot of the time we've been considering time stepping problems or first order differential equations that are defined by their initial values. Now we're considering boundary value problems, second order differential equations that are defined by their boundary conditions, or if you like, two constants of integration. So in this case, if we have a domain in x now in space going from 0 to 1, we have the two boundary conditions. Y is 0 at both the endpoints. So the analog here, say, if we take an analog from engineering, is if you have say a beam or something like that, doesn't really matter too much, and it's been applied a force on that beam and it's suspended by 2 points, and you're just trying to calculate the solution for the beam in between these 2 points. So that's the analogy. So. And we discretize that with a second order formula from Taylor's series. Remember, we've got these coefficients 1, minus 2 and 1. You need to really remember these. They're very common for the second order approximation for the second derivative. And delta x now is the grid length, right? It's very important to get that notation right. Let me just emphasize that. So delta x is the grid length, and it's the way we chop up the x domain, and the notation is delta x. Okay, so hopefully we're fully out of the habit of using this notation of h now. I don't want to see it on any solutions, please. We use delta for change, x because it's on the x-axis, so in the same way we use delta t for the time step. Okay. We rearrange that, and then we realize that the only way to satisfy the boundary conditions and this second order differential equation is to form a matrix equation. So this is very different from many of the ordinary differential equation methods we covered, although you can have matrices in those methods as well at times. So this is our first encounter, if you like, of using matrices with ordinary differential equations. And it's an example where, you know, I compartmentalize this term's work into roots, ordinary differential equations, matrices, and optimization. But that's a compartmentalization we come up to try and learn the subject. But actually, when you understand things a bit deeper, you realize that actually the matrices, in this case, links in with the ordinary differential equations. The roots fits in with optimization. It all sort of should form a sort of nice mesh of knowledge. Anyway, that's by the by. That's just a comment on compartmentalization in university learning. But the main thing was we have this matrix, which in its middle points, 1 minus 2 encapsulates this second order derivative. Yeah, because the coefficients 1, minus 2, and 1 correspond to 1, minus 2, and 1 in the interior points, and we use dots just to show that that's repeated. And then we have the boundary conditions that are y0, so the index goes from 0 to n minus 1. Okay, in this case there's big n points, and we go from 0 to n minus 1, and 1 times y0 is 0, and 1 times yn minus 1 is 0. So the matrix encapsulates these two things, the boundary conditions plus the second order derivative centered difference approximation. It puts it all together, then you invert the matrix, and then you have your answer. So we're now going to just go over to our MATLAB in a minute to look at a a worked example. So we're going to look at the case where if we have d2y by dx squared is sine x, so basically I've called f on the right hand side, our function is the sine x now. We can actually, and we are on a domain now of 0 to pi because that fits best with a sinusoidal function. And we have, okay, so these boundary conditions where we specify the value of y has a name, and it will come up in other applied topics. It's called Dirichlet, after the person who used them first, maybe, or used them a lot. So Dirichlet comes up in other areas of mathematics, his name. And basically that's you giving the value, and that's the one we're gonna use here. Just for reference, the other type of boundary condition is called Neumann boundary condition, is where you specify the first derivative of the boundary condition. So rather than y and at either end, we specify dy by dx, but we're not going to deal with that case today. But some of the examples and in the coursework, and sometimes and in the tutorial examples and exam questions, you'll come across that as another type of case. So the good thing about this case is that we can easily come to the true solution. So the true solution is y. So we've got y star equals minus sine x. I'm just going to scroll on the sheet so we can check that. So we have d, just do a bit of differentiation of sine, nice and easy. It's minus cos x, and then d2y star by dx squared equals sine x, which is our original equation. Right, so that's just, I've just verified by substitution that true solution is this one. So I picked a domain 0 to pi that works easily because sine is 0. Basically it means the forcing function is 0 at either end, and the true solution that fits it is minus sine x. So we've got a nice simple true solution that we can then check our sort of matrix method against. Okay, so, and the problem we're going to look at is in a code called boundary value.m that is on the LE page for this week, and then the LE pane first thing, and I'm going to go through that code now. So let's move over to the MATLAB code. And what I'm going to do is just move windows around so things are clearly in the middle of the screen. And get rid of my scrollings here. Let's do that. There you go. So this is a code boundary value.m. Let's just move it down a bit again. And let's just go through fairly simply through the steps. So I'm going to we'll try and write down on the right hand side the notation used in the theory, because it's one of the problems of sort of problem solving with code, which is one of the things I think we do rather than just learning how to code, is making that translation between what's used in the code. So so basically your thing, big N goes to nx. Okay, so that's what I've chosen for nx. So that's the number of points in x, and this time it's a very small number. In fact, I'm just, for the first time of running this, I'm just going to change it back to a large number, and then we'll have a look at doing a small number in a minute. So that's nx is 51. Let's just go back. So this you could put this together in a live script if you wanted to, if you're interested. So n goes to nx, and that corresponds to the big N here, the number of points in the x direction that we're going to invert. Then we have dx, so that's that corresponds to delta x. So delta x is simply written as dx in the code. And that's basically the length of your domain, pi, divided by the number of points. So the number of points, pi divided by the number of gaps. Okay, so is n minus 1, and it's the number of spaces. Right, it's just a ladder problem. If you have 3 points on a ladder, you have 2 spaces, yeah? So if you have n points like we have here, or nx points, we have n minus 1 spaces, and that's your grid length, yeah? Which is dx. Okay, so that set things up. Then we set up an array here for x, which goes from 0 to pi, and it's spaced by dx. So dx is our grid length, delta x. I've already stated up there. Let me just get rid of the scrawlings again because they don't correspond to anything now. So I move down. Okay, so I've also set up another array, this x underscore t, which is going to be for the true solution. Because I want to vary our delta x, which is basically our discretization of a numerical method, but I don't want it to change for the true solution. So I do set up a similar grid length dxs in this case for the true solution. I'm going to use 100 points, and then a similar x-axis. So that's just separately for the true solution. And then we do the right hand side, so we're going to call it B, because often we write down in a matrix problem as x equals b. So B is the right hand side corresponding to f, to the right hand side. So it's basically it's delta x squared times f, and f in this case is simply sine x. Yeah, that's the right hand side. So it's dx squared plus times sine x. Now don't sometimes to set this up, we've got to be careful whether we're dealing with a row vector or a column vector. So let me just show you in MATLAB. If we have, if I have a vector, like, just call it A equals 2, if I just put in an array like that, it normally comes across, you see the numbers are written as a row vector. But actually what we need to plug this into our matrix inversion problem is a column vector. So we do the transpose. And remember, the transpose is very compact notation in MATLAB. It's sometimes too compact. It's a shame it's not something like T, but it's the inverted comma. And don't forget about this. That means you're transposing it. So we're converting what would be a row vector of values into a column vector. So by gaining B, going back to our theory now, you can see why these we're basically generating all those values on the right hand side. So this turns out to be B in the code. So all this corresponds to B vector, if you like, column vector B. Okay. And then we need to set up our matrix A. I've called it A in this case, but that A is T. It's the same as T. So let's just write that down. So our T matrix goes to A in this case. And that's just, I've just set it up as a zeros matrix with size nx by nx. So that's an m by n matrix. M by m matrix. Okay, and this is going to be just going back to the theory. Get rid of that. This is what we call A in our code. So we got A, and we're going to actually, I don't. Okay. So what I'm doing quite a lot is translating the mathematical statement to the code statement. And if you're struggling with the code at all, especially more complicated one, I'd always advise doing that. Get the maths out before you, even if it's not in a live script where we've got it all together. Just have the maths on one side and the code on the other, and either print out the code or scribble on it, you know, virtually with on your PDF. But somehow try and just make sure you understand what bit corresponds to what on the code, and that then breaks down a big barrier in terms of understanding how the code works, right? So that, it's a little bit like understanding notation before you proceed with the proof. If you don't know the notation that's used in the proof, you're never going to do it. In coding and problem solving with coding, which is what we're doing here, then understanding all the terms near the top of the code helps understand the contents of the code. So then we now need to define this matrix A, and the first thing to do is define these inner points, which are 1, -2, 1. Okay. So basically we just construct a loop from 2 to nx minus 1. So that's for all the interior points. Okay, so that all the points run from 1 to nx, but of course the end points are occupied by 1, 1. Okay, so there's a slight other thing here, is the indexing in the way I've written down the method goes from 0 to n minus 1, but of course the indexing in MATLAB goes from 1 to nx in this case, so you have to make that translation as well, and you know, that's not an uncommon thing to do as well, so get used to. So this is our interior points, and basically the format for A is in row column format. So let's just remind ourselves about that. So we have A, row, column, index. Of course, those are indexes. So this so the central one, which is the diagonal, so that's the diagonal, is I, I. And then the two other ones, the off diagonal, and you can see it corresponds exactly to the diagonal. So this is our diagonal. And then you've got 1, 1 of the off diagonal elements. Yeah. And those are filled in 1, -2, 1. And then the final thing is to fill in the boundary conditions, which are these 1s at the corner. So that corresponds in MATLAB. Remember, this is index 0 in the method, but that corresponds to index 1 in the MATLAB, and then nx, n. So those are the boundary conditions we fill in, and then finally we just invert it to find the solution, y = a / b. Okay, so that's a very important thing in MATLAB to get used to. It's very compact again, but this solves a, y = b, and it's a, so the syntax is y = a / b. Now, don't be deceived by the simplicity of this bit of notation in MATLAB. That underneath that is a huge amount of coding effort. Arguably, it's the crown jewels of the MATLAB code. One of the things that works very well in MATLAB is its matrix inversion routines. So we're benefiting from that by just putting a / b, not a / a /. Okay. And then we just plot out the solution, the numerical and the true solution. So let's just run it. Okay, and what I'm going to do is just get rid of this PDF for the time being, and just look at the window now. So this is what you get. So I encourage you just to download this and run it yourself. Change the number of points, and what we have here is this true solution, which was simply minus sine x which is just given by the dotted, and this is a true solution evaluated at each grid point uses. Remember, we're using 51 points here, so a lot of points. And then it turns out the numerical solution is very close to the true solution in this case, which is good. And it's because we're using a large number of points, a small grid length. Remember, the error in this method is all to do with this second order truncation error. So, you know, it's this order delta x squared term that comes in the expansion that causes the error. So the smaller delta x is, i.e. the larger the number of points, so it's a larger number of the points, means that you have smaller delta x, and it goes as delta x squared. So actually it's shown here that because the true and the numerical solution look almost identical here, it's because this truncation error is very small. So that's good. That all ties together our sort of theoretical view. Now we can test this further by trying to increase delta x and decrease the number of points. So here dx is just 0.0628. If we now decrease the number of points massively to 6, so that means increasing delta x, and then rerun it and see if it works. Now you have to ask a question, is it going to work so well now we've got a bigger delta x? And the question is no, it does all right actually. But you now see the true solution I've kept on a high resolution grid. So we've got all loads of points, but the numerical solution is now only has 1, 2, 3, 4, 5, 6 points. So it gets the boundary conditions right, it gets the general shape, but there are big differences now in between the numerical solution and true solution as you get here. So that's your truncation error. Okay. And you could do this quantitatively. You could just evaluate the difference between the true and the numerical solution for a whole range of delta x, and then plot them up. And you should be able to then infer what the truncation error, which is order delta x squared. So you should be able to get a delta x squared dependency on the truncation error if you did like that. Okay. Okay, so that's really finishing off the ordinary differential equations section, but it meshes quite nicely now with the matrix method. So in the next video we'll get started again with matrices. We'll revisit things like Gaussian elimination. I'll go through that very briefly, but then we'll actually want to see that when we do Gaussian elimination, we actually come across something called LU decomposition, which will probably be new, and then we'll move on from then into the world of matrix methods. Okay, I'll see you next time.